deal with them.
Today's lesson, section 8.5, we're really going to be taking what we learned in the previous two sections, 8.3 and 8.4, and now we really start to apply it into some important stuff. We're going to be solving functions that are either exponential or log, and we're going to need that prior information in order to do this. So hopefully you understand things like how to evaluate a logarithm, how to change from exponential to log and vice versa, and those properties that we learned, those three properties are going to come into play as well as we learn how to solve equations. So let's just jump right in. You're going to need your calculator, so if you don't have it, I'll give you a chance to grab it. What I've done here is, for the most part, this assignment is going to be you doing the evens. For the most part, I'll show you one or a few exceptions to that. So what I've done is I've picked some odd problems on your homework page to work through, and hopefully this will help you with the evens that are pretty close to these. Okay, so on page 456, which is where your homework assignment is located, I have written down problem number 1 from your book, which represents an exponential equation. It's exponential because I'm trying to solve for x, which is the exponent. Okay, so solving for the variable when it represents the exponent in this equation. So here's the deal. Here's the big takeaway from this lesson. If you are given an equation that is in exponential form, it's known as an exponential equation, immediately you need to change those into log equation form. Okay, so I don't really care if you write the problem down. Some people like to. The red would be what the book gives you. I do want you to show how that exponential equation would look as a log equation. So that needs to be part of showing your work. Okay, now that we're in this log equation form, hopefully you understand how we got from red to blue. Now you're going to use your calculator, and we're going to use what is known as the change of base formula. And the change of base formula is pretty simple. You need to find the log button on your calculator, and you're going to end up pressing it twice. You're going to do log and then the top number, which is 3. Now, if you have one of those calculators that automatically displays the left parenthesis, you're going to have to enclose it with the right. That will mess up your answer if you don't. Okay, so you've got log 3 divided by, now you're going to press the log button again and put in the bottom number. So it's easy to remember because the top number is the numerator, log 3, divided by log of the base. And for all of your decimal answers on this assignment, you're going to be rounding to the 4th decimal place, the 10,000ths. And I just want to make sure, verify that everyone was able to come up with this rounded answer. So did anybody not get that? Some of you have calculators where you have to go backwards. You have to put in the number, then log. So I just want to make sure we're all good. Any questions? Looks like no one has a question. Everyone was able to get it. Okay, let's try another one. This is number 3 off of that same page. This is an exponential equation. So I need to change it into log form. So in log form, log equation form, this is going to be log base 5. 5 is the base of the exponent of 81.2 equals our exponent. Remember, logarithms are exponents. So when you're writing the log form, always let log equal the exponent. Now you're going to use that change of base formula again. Log of the top number divided by log of the base. And since we're rounding, I'll do a approximately, and who has that? Thomas, what'd you get?
2.73.
Okay, and all of these you're going to round to the fourth decimal place. So there'll be one exception to that. It's going to be a word problem that I'm going to work with you in just a minute. But the other equations like this, you'll just round to the 10,000s. All right, any questions on number 3? It's crucial that you understand that exponential gets changed to log form, and then you immediately you're able to use your change of base formula. Number 9 is a little different. We approach it the same way. Raise your hand if you'd like to tell us how to put this in log form. It's an exponential equation. What would this look like in log form? Okay, go ahead. Well, we will eventually, but we first have to show the log form of the equation. Did you say common base or change of base? Okay. Yeah, what we're doing today is called the change of base. But what would this look like as a log equation? Good? Nice. Okay, I want you to take a few seconds and use the change of base formula. And I wonder if someone would volunteer what that is. What is that, Dalton? 1.2056. Okay, still haven't solved for y, but it's pretty easy to get there. What do I need to do to solve for y? Add 2. All right, so my answer for y, and we'll do approximately since we rounded, but we just add 2 to both sides. Okay, any questions so far? Exponential form, change to log form. Okay, I thought I would give you a little bit of help on this word problem. There's one word problem on tonight's assignment, and it's very much like this. I put the essential information in red, so you can kind of cut down on your notes. Everything in red, just capture in your notes. And I basically took the book's number 31 and just put in my own numbers. So if you'll follow what we're doing as a model, you should be really good to go on your homework problem number 31. Okay, so the reason why I'm using this formula for compound interest is because it's not compounded continuously. Notice this is quarterly compounding. The only time I use the continuously the PERT formula is when it said it compounded continuously. Any other types of compounding, we use this compound interest formula. All right, so what we have here is an initial investment of $4,000 became $5,000. So we're told basically what A is, because A represents what did the investment become after interest was applied. So A in this case is 5,000. And P stands for principal. It means how much did you invest? Well, we invested 4,000. 1 plus the rate as a decimal, 4.25%. Remember, you always need to change that to decimal form. N stands for how many times during the year will compounding happen. And since it's quarterly, that means N is 4 times a year. N again will be part of your exponent, but it needs to be multiplied by T, which stands for number of years. Well, that's what we're supposed to find. We're looking for T. So the first thing I need for you to do is use your calculator and come up with the parenthesis. What is that value? 1 plus 0.0425 divided by 4. Okay. Who's got that? Lauren, do you have that? 010625. Okay. Everybody good on that? Well, eventually we're going to create an exponential equation like we were working on previously. Just some number raised to a power that equals x. Okay? Or some number raised to a power equal another number. And I'm close to having that here. I just have to undo multiplying by 4,000. So I'm going to divide by 4,000 on both sides. And to save a little bit of time, you could do 5,000 divided by 4,000, but it's 1.25 is equal to 1.01065 raised to the 4t power. Well, the great thing about knowing how to solve these exponential equations using logs is we now know how to find out how many years was involved. I need to change this exponential equation into a log equation. So what's that look like? What does this exponential equation look like as a log equation? You get, how about Mackenzie? Okay. Okay. Nice. All right. Well, what's going to happen next? What did we learn on the previous slides? What's our formula called? Change of base formula. So now in your calculator, you're going to do log 1.25 divided by log 1.010625. I'll write that down. And what is that? Adam.
The nearest 10.
Let's just go ahead and we'll round at the very end.
5.2782.
Okay. Everybody agree with that?
Oh, at the end. Okay, it's 21.1131. I already gave you the divided by 4.
So it's 5.2782. What else?
No. That's the 21.1131.
Ah, okay, I got you.
There we go.
21 point what?
1131.
Equals 4t. Everybody with me? So how did you solve for t?
I just divided by 4.
Okay, and rounded to the nearest tenth, it should be approximately 5.3 years. T stands for a number of years. So what we're saying is $4,000 in 5.3 years at that interest rate compounded quarterly would grow to $5,000. All right, so any questions on that word problem? I think I've set you up pretty well for later. Okay, when we get to number 33 and following, notice how our equations change. We are now not solving exponential equations. We are solving log equations. Notice the word log in the equation. So you guessed it. Now we're going to go in reverse. Log equations have to be changed into exponential equations. So it's just the reverse of what we were doing previously. So somebody give me the exponential equation of the form, the exponential form of that blue log equation. Maybe Jessica. Now an exponential equation will not have log. It's just some number raised to a power equals another number. So what's the base? 10, okay, raised to the -1 equals, nice. And what's the fraction form of 10 to the -1? Brianna. 1/10. Just change 10 to the -1 into 1 over 10, and it's pretty easy now to solve for x. How do I solve for x? You could, but that might scare some people. If I divide by 2,
Multiply it by 2's reciprocal.
Okay, which is? Yeah, I like that better. Let's multiply by the reciprocal of 2, the old multiplicative inverse property. Say that again?
It says technically dividing with fractions, is it not? I mean,
Dividing by a fraction is like multiplying by its inverse.
Yeah.
You're right. And now let's get the decimal form of that. What's the decimal form of 1/20th? 1 divided by 20. Any questions? So log equations get changed to exponential form. Okay. Virginia, 35. What would this log equation look like as an exponential equation? Okay. Nice. Well, 10 to the second is just, so that looked kind of scary to begin with, but it turns out it's a pretty easy equation. Subtract 1, divide by 3, and got our answer. Log equations get changed to exponential equations. All right, just got a couple more examples, and that will wrap this lesson up. Before I can get to exponential form, exponential equation form, then I've got to apply this power property rule. I've got to move, or I've got to clear the space in front of log. And so you remember this from a few days ago. My first move is to change this factor of 3 into an exponent 3. Okay, so Jordan, can you give me the exponential equation? Well, exponential equations don't have log. It'll be some number raised to a power equals another number. So what's the base? What's the base of the log? Okay, so the base of the exponent will be 10. What will the exponent for 10 be? Okay, and he said 1.5. He's correct. I'm just going to write it as 3 over 2. It's okay if you didn't. I'll show you why in just a minute. 10 to the 1.5 or 1.5 power is going to equal what? X to the third. Well, I need to solve for x. Or in other words, I need to solve for x to the first. Any ideas on how I can mathematically change x to the third into x to the first? Yeah? Cube root. And we learned in chapter 7 that another way of saying cube root using an exponent is the 1/3 power. It's the same thing as the cube root of both sides. But if I raise the right side to the 1/3 power, I also have to do the left. So we got x to the first on the right. What does this become on the left? 10 to the what power? 3 over 6, which is 1/2. And what's the radical form of 10 to the 1/2? Square root of 10. So grab your calculator And let's find the decimal equivalent rounded to 4 decimal places for the square root of 10. So let's see, who's got it? Okay, go ahead. You got it? Okay, so rounded to the 4 decimal places would be 3.1623. Got one more. Last example. Then I'm going to set one up for you. We won't finish it, but I'm going to set it up. Let me see. I'm going to get Anna. Here's the deal. Before I can write exponential form, if my equation contains multiple logs, I have to use the properties to put it together as a single log. So we've got properties that help us do that. Which one will we apply here? What will this look like to take these 2 separate logs and combine them into one? Okay, sounds like she described the quotient property, which says 2 separate logs being subtracted, as long as they have the same base, can be put together as a single log using division. So now, Anna, we're ready to put this in exponential equation form. Nice. Very good. And it's a pretty easy equation to solve. I'm going to multiply by 2x on both sides. Just clear the fraction on the right because the result over here on the right side will just be 5. On the left side will be 20x. Divide by 20 on both sides gets us to our answer, which is 1/4. Okay, I want you to write the assignment, and then I'm just going to set up number 6 because it gives people some fits. It's a little different, so I'm going to set it up for you, and I'm going to let you finish it. The thing that makes number 6 a little different is it's not already in exponential form, meaning some number raised to the x equals another number. We've got to do a little bit of work first. I've got to isolate 3 to the x power. And this, some people get to this point and they think, I've never seen log of a negative base before, and that's right. There should never be log of base negative. But if I divide or multiply by -1 on both sides, that'll take care of that. So now you're ready to go. I just gave you some help getting you to a point where you can now change it to a log equation and use your change of base formula. So let me know if I can help you. We'll check them out tomorrow.